Hello everyone, welcome to our lecture on data science, exploring data. Today we will be covering chapter 3, focusing on the essential practice of data exploration in the data science workflow. Data exploration is a fundamental step in the data science process. It involves examining and understanding the characteristics of your data before applying more complex analysis techniques. This preliminary step helps us become familiar with our data and identify patterns or issues that might affect our analysis. So what exactly is data explorations? There are several key motivations for exploring our data. First, it helps us select the right tool for pre-processing or analysis. Second, it leverages human natural ability to recognize patterns that might not be captured by automated data analysis tools. Data exploration is closely related to exploratory data analysis, or we call it EDA, which was developed by statistician John Tukey. Technique used in data explorations. In traditional EDA was defined by Tukey. The focus was primarily on visualization, clustering, and anomaly detection were also considered exploratory techniques. However, in modern data mining, clustering and anomaly detection have evolved into major areas of interest in their own right, rather than just exploratory methods. So in our discussion today, we will focus on three main techniques used in data explorations, such as summary statistics, visualization, and online analytical processing, or we call it OLAP. Iris sample datasets. Many of the exploratory data techniques we will discuss today will be illustrated using the iris plan dataset. This dataset can be obtained from the UCI machine learning repository at the URL shown here. The dataset was created by statisticians Douglas Fisher and contains data on three different types of iris flowers: Setosa, virginica, and versicolor. For each flower, 4 attributes are measured: sepal width and length, and petal width and length. The image on the right shows an example of the virginica iris flower. Summary statistics. Summary statistics are numerical values that summarize property of the data. These properties typically include frequency, locations, and spread. For example, the mean is a measure of location, while the standard deviation is a measure of spread. One of the advantages of summary statistics is the most can be calculated in a single pass through the data, making them computationally efficient. Frequency and mode. The frequency of an attribute value is the percentage of time that value occurs in the dataset. For instance, in a representative population, the gender female occur about 50% of the time. The mode of an attribute is simply the most frequent attribute value. Both frequency and mode are typically used with categorical data, which we are dealing with distinct category rather than continuous value. Percentiles. For continuous data, the concept of percentile is often more useful than frequency, given an ordinal or continuous attribute x and a number p between 0 and 100. The percentile is a PTH. Percentile is a value of x such that p percentile if of the observed value are less than the value. For example, the 50th percentile is the value below which 50% of our value fall. Percentile gives us a way to understand the distribution of our continuous data. Measure of location, mean, and median. Measures of wait. When we talk about the location of data, we're referring to its central tendency. The mean is the most common measure of location, calculated as the sum of all values divided by the number of values. However, the mean is very sensitive to outlier extreme value that can skew the result. For this reason, the median, which is the middle value when all values are sorted, is also commonly used as it's less affected by outliers. Another alternative is the trimmed mean, which removes a certain percentage of the highest and lowest value before calculating the mean. Measures of spread, range, and variance. Measures of spread tell us how dispersed our data is. The simplest measure is the range, which is the difference between the maximum and minimum value. The variance and its square root, the standard deviation, are the most common measures of spread. They quantify how much the value deviation from the mean, like the mean. However, variance and standard deviation are sensitive to outliers, so other measures like interquartile range are often used when dealing with data that might contain extreme value. Can only display so many points when selecting objects. Parallel coordinates plots for visualization. Visualization is the conversion of data into a visual or tabular format that allows us to analyze the characteristics of the data and the relationships among data items or attributes. It's one of the most powerful techniques for data exploration because humans have a well-developed ability to analyze large amount of information presented visually. Through visualization, we can detect general pattern and trends, as well as identify outlier and unusual pattern that might not be apparent from summary statistic alone. Example, sea surface temperature. This slide shows an example of visualization in action. Here we see the sea surface temperature for July 1982. This single figure summarizes tens of thousands of data points, allowing us to identify temperature patterns across the world's oceans at a glance. Notice how the visualization makes it easy to see warm and cold regions as well as temperature gradients. Representations. In data visualization, representation refers to the mapping of information to a visual format. Data objects, their attributes, and the relationship among them are translated into a graphical elements such as points, lines, shapes, and color. For example, objects are often represented as points, with their attribute value determining the position of this point or their characteristic like color, size, and shape. When positioning is used to represent attribute values, relationships between points, such as whether they form groups or if a point is an outlier, become easily perceptible. Arrangement. Arrangement is the placement of visual elements within a display. The way elements are arranged can make a significant difference in how easy it is to understand the data. A good arrangement can highlight patterns and relationships, while a poor arrangement can obscure them. The choice of arrangement depends on the nature of the data and what we want to emphasize in visualizations. Selections. Selection involves the elimination or the emphasis of certain object and attribute. That this might include choosing a subset of attribute to focus on, often through dimensionality reduction to reduce the number of dimensions to 2 or 3 that can be easily visualized. Alternatively, we might consider pairs of attributes. Selection can also involve choosing a subset of objects us a region of the screen can only display so many points. When selecting objects, we might sample the data, but we want to preserve points in sparse area to maintain a representative view of the data distributions. Visualization techniques are histogram. One of the most common visualization techniques is the histogram. A histogram shows the distribution of value of a single variable. It works by dividing the value into bins and showing a bar plot of the number of objects in each bin. The height of each bar indicates how many objects fall into that bin. It's also important to note that the shape of a histogram can depend on the number of bins chosen. Too few bins might obscure important details, while too many might create a noisy visualizations. Two-dimensional histogram. While standard histogram show the distribution of a single variable, two-dimensional histogram show the joint distribution of a two attribute. This example shows a two-dimensional histogram of a petal width and petal length from the iris dataset. By looking at this visualization, we can see how these two attributes related to each other and whether there are any pattern in their combined distributions. Visualization techniques. Box plots. Box plots invented by John Tukey provide another way to display the distribution of data. The basic components of a box plot include the median, show us a line within the box, the quartile which define the box, and potentially outliers shown as individual point beyond the whisker. Box plots give us a compact summary of the distribution center, spread, and shape. Example of box plots. This slide shows how box plots can be used to compare attributes. Here we see box plots for different attributes of the iris dataset, allowing us to compare their distribution at a glance. We can quickly see which attributes have greater variability, whether they are systematically distributed, and if there are any potential outliers. Visualization techniques. Scatter plots. Scatter plots are another fundamental visualization technique. In a scatter plot, the value of two attributes determine the position of points on a two-dimensional plane. While two-dimensional scatter plots are most common, three-dimensional scatter plots are also possible. Additional attributes can be displayed by using the size, shape, and color of the marker that represent the objects. Arrays of scatter plots can be used to compactly summarize the relationships of several pairs of attributes. Scatter plot array of iris attributes. Here we can see this slide shows a scatter plot array of the iris dataset. Each cell in the array shows a scatter plot for a pair of attributes, with the diagonal showing the distribution of each individual attribute. This type of visualization allows us to see the relationship between all pair of attributes in a compact format, making it easy to identify patterns and correlations. Visualization technique. Contour plots. Contour plots are particularly useful when a continuous attribute is measured on a spatial grid. They partition the plane into regions of similar value with contour line connecting points with equal value. The most common example is contour map of elevation, but contour plot can also display other spatial data like temperature, rainfall, or air pressure. Contour plot example SST, December 1998. In this slide shows here a contour plot of sea surface temperature for December 1998. The contour line connected point of equal temperature, allowing us to see temperature pattern across the ocean. Regions between contour line represent area with similar temperature value, and the density of the line indicates how rapidly the temperature change in that region. Visualization technique, matrix plots. Matrix plot can be used to visualize the data matrix itself. It can be useful when objects are sorted according to class, as patterns might emerge that were not apparent before. Typically, the attributes are normalized to prevent one attribute from dominating the plot. Metric plot can also be used to visualize similarity or distant matrices, which can help in understanding the relationship between objects. Visualization of the iris data matrix. As you can see here, the iris data matrix, each row represents an iris flower and each column represents an attribute. The flowers are sorted by class, which help reveal pattern in the data. The color represents the normalized attribute values, making it easier to see similarity and difference between the flower. Visualization of iris correlation matrix. In here we see coordinates are used to plot the attribute value of high-dimensional data instead of using perpendicular axis as in traditional plot. Parallel coordinate use a set of parallel axes. The attribute value of each object are plotted as a point on each corresponding coordinate axis, and these points are connected by a line. Thus, each object is represented as a line across all the parallel axes. Often, lines representing objects from the same class will group together. At least for some attribute, the ordering of attribute is important in seeing such grouping. Hello everyone, welcome to our lecture on data science. Parallel coordinates plots for iris data. In this slide shows parallel coordinate plots for the iris dataset. Each line represents a single iris flower. When its position on each axis represents the value of that attribute. Notice how the line of each class of iris tend to follow similar path, indicating that there are patterns in the attribute values that distinguish the classes. Other visualization techniques. Well, there are several other visualization techniques worth mentioning, like star plot use a similar approach to parallel coordinate, but with axis radiating from a central point. The line connecting the value of an object forms a polygon. Chernoff faces created by Hermann Chernoff associate each attribute with a characteristic of a face. The value of each attribute determines the appearance of the corresponding facial characteristic, so each object becomes a separate face. This approach relies on human natural ability to distinguish faces. Star plots for iris data. This slide shows star plots for the three classes of iris flower. Each star represents the attribute values of a single flower, with the length of each ray indicating the value of that attribute. By comparing these stars, we can see the characteristic pattern for each class. Chernoff faces for iris data. Here we see Chernoff faces for the three classes of iris flower. Each face represents the attribute value of a single flower with different facial features corresponding to different attributes. While this approach might seem unusual, it can be effective because humans are naturally good at distinguishing faces and noticing subtle differences between them. Move on, we have OLAP, Online Analytical Processing, or we call it OLAP, was proposed by E.F. Codd, who is known as the father of relational database. While relational database put data into table, OLAP uses a multi-dimensional array representation. This type of data representation has existed in statistics and other fields for some time. There are several data analysis and exploration operations that are easier with this multi-dimensional representation, by the way. Creating a multi-dimensional array. Converting tabular data into a multi-dimensional array involves two key steps. First, we need to identify which attribute will be the dimensions and which attribute will be the target attribute, whose value appear as entries in the array. The attribute used as dimensional must have discrete value, while the target value is typically a count or a continuous value. In some cases, there might be no target variable other than the count of objects that have the same set of attribute values. Second, we find the value of each entry in the multi-dimensional array by summing the value or counting all objects that have attribute value corresponding to the entry. Example iris data. To illustrate how to create a multi-dimensional array, let's use this iris data. We will use petal length, petal width, and species type as our dimension. First, we discretize the petal width and length to have categorical value, low, medium, and high. This gives us a table with a count attribute as shown here. Example iris data. Each unique tuple of petal width and species type identify one element of the array. This element is assigned the corresponding count value. The figure illustrates the result with all non-specified tuple being 0. This multi-dimensional array representation makes it easier to perform certain types of analysis on the data. Slices of the multi-dimensional array are shown by those crosses tabulations. This table shows the counts for different combinations of the dimensions. By examining these slices, we can start to see patterns in the data, such as which combination of petal width and length are most common for each species. Moving on, we have OLAP operations, data cube. The key operation in OLAP is the format of a data cube. A data cube is a multi-dimensional representation of data. Together with all possible aggregates, by all possible aggregates, we mean the aggregate that result from selecting a proper subset of the dimensions and summing over all remaining dimensions. For example, if we choose just the species type dimension of the iris data and sum over all other dimensions, we get a one-dimensional entry with three values, each giving the number of flowers of each type. Data cube example. This slide shows an example of a data cube for sales data. The original data can be represented as a three-dimensional array with 3 dimensions for product, location, and date. From this, we can create various aggregates. There are 3 two-dimensional aggregates, one for each pair of dimensions, 3 one-dimensional aggregate, one for each individual dimension, and 1 zero-dimensional aggregate, the overall total. Data cube example continue. This figure shows one of the two-dimensional aggregate along with 2 of the one-dimensional aggregate and the overall total. This aggregate allows us to view the data at different levels of granularity depending on what aspect we want to focus on. Slicing and dicing. Slicing and dicing are operations that allow us to focus on specific parts of the data. Slicing involves selecting a group of cells from the entire multi-dimensional array by specifying a specific value for one or more dimensions. For example, we might slice the cell data to look only at cells for a particular product. Dicing involves selecting a subset of cells by specifying a range of attribute value, which is equivalent to defining a sub-array from the complete array. In practice, both operations can also be accompanied by aggregation over some dimensions. Attribute value often have hierarchical structure. For example, a date is associated with a year, month, and day. A location is associated with continent, country, state, and city. And product can be divided into various categories. This category often nest and form a tree or lattice structure, with year containing months, which contain days, and country containing state, which contains city. Roll up and drill down. This hierarchical structure gives rise to the roll up and drill down operations. Rolling up involves aggregating data into a higher level of the hierarchy. For cell data, we could roll up the cell across all dates in a month to get monthly total. Conversely, drilling down involves breaking down data into a lower level of hierarchy. Given a view of data where the time dimension is broken into months, we could drill down to see daily sales total. We can perform similar operation on other hierarchical dimensions such as locations or product category as well. Well, that includes our exploration of data exploration techniques. We cover summary of statistic variance visualization method and OLAP operations. These techniques form the foundation of understanding your data before dividing into more complex analysis. Well, remember, effective data exploration is an iterative process. As you learn more about your data, you may need to revisit these technique with new insights or questions in mind. Well, thank you for your attention and hope you have a good one.